Okay, I think with that, we have everyone settled here and our logistics taken care of. So I'm Sri. I'm a coach for FRC Team 9023. And here beside me is Rohan, who's the president for Future Martians this year. Can go ahead and take it from here.
Yeah, hello everyone. Thank you for attending this FLL coding camp. We've been running, this is our third year running this now, so should be good. All right, so I'll start by just introducing who we are. So we're a fourth year FRC team. Our rookie year was in 2023. So we've mentored over 35 FLL teams in the past 3 years. And most of our students on our team have experience in FLL and FTC and worked their way up to FRC now. We made it to World Championships during the season twice in our 3 years. So we'll now start with just a Spike Prime overview.
Okay, my name is Isha. I'll be going over the hardware. The brick is the robot's brain, and it controls all the motors and sensors connected to it. It also has a 5x5 customizable light matrix, a speaker, and it stores up to 20 programs. The brick has 6 input/output ports along with a built-in gyro sensor, and it also has Bluetooth and micro USB options for connection.
This point, I know we kind of just jumped in here, and the expectation was that for this camp, you would have potentially already done 1 year of FLL maybe, because we're trying to teach advanced coding, but maybe you've started over the summer and you've already learned some stuff and you're ready for advanced coding, and that's fine too. As most of you have, either in your first year of FLL, or if you've been learning, you probably already worked with the brick. And before we jump into motors, just wanted to add that if you have any questions, feel free to put it in the chat, or please ask. You can also raise your hand. I think we can have, actually, raising the hand might be harder to see. So please go ahead and, unmute yourself and you can ask the question, or you can put it in chat. We have members here looking through chat. We have about 6 FRC team members here, and we have a few students in person. So please don't hesitate to ask questions, because we want this to be helpful to you as you get started on your new season with some advanced coding techniques. We have usually gone through an introduction, but I know there's a lot of people who have, or a lot of students who have signed up. So you guys will have a few lighthearted moments, maybe some introduction when we break into lunch. But for now, let's go ahead and continue.
Okay, moving on to motors. There are 2 types of motors, medium and large. The medium motors are for lighter loads, and they have a higher max speed than large motors and are very compact. To use them as drive motors, you do need a lighter robot. The large motors are for high power, high torque applications, but are larger and slightly slower than medium motors, so they would make better drive motors for heavy robots. Now, moving on to sensors. Distance sensors detect how far an object in front of it is. They have a range of 200 centimeters. Force sensors detect the amount of force being acted on them, up to 10 newtons, but they can also be used as touch sensors. Color sensors measure reflected light, along with being able to distinguish between 8 colors. Rotation sensors are built into the motors, and there's also a built-in gyro sensor, which we will cover next. Okay. Now for the gyro sensor. The inbuilt gyro sensor has a 3-axis gyroscope and a 3-axis accelerometer. The gyroscope can measure the pitch, roll, and yaw angle of the Spike Prime brick, and can also determine the orientation, front, back, top, and bottom, and more. The accelerometer allows gestures to be detected, such as a shake, a tap, or a free fall.
So let's take a moment to talk about what was covered here. First, we spoke about the brick, and I think you all are if you put a robot together, you know how the connections are made to the brick. Sensors as well as motors all get connected to any of those 6 ports. And one thing important to remember there is when you have the 2 motors which are driving the robot, you call them the drive motors or the movement motors. And you need to be aware of which are the 2 ports that correspond, that is for the left and the right of your robot, of those ports. Because when you code, you need to be able to provide the movement motors. So please remember which ports are specific to your robot. So for those of you who are remote, if you have a robot that you're planning to run this on, please make sure you are aware of the 2 ports where you have the movement motors connected. That's one. And then we spoke about the types of motors available. Now you have the large motors and the smaller motors. Some teams use the large motors for moving the robot, and some teams use it for moving the attachments. And there's no right or wrong. It's just really how you built your robot and whether it's a light robot, whether it's a heavy robot. And then when you're moving attachments, is it a light attachment or do you have multiple gears going? So do you need more torque? Torque is basically the strength applied, how much force is being applied to whatever system is attached to those motors. So when you have a heavy robot, definitely use the larger motors to move the robot. And then when you have attachments that need a lot of torque, then you should be using the large motors for the attachments. And then for sensors, color sensors are pretty useful. And then the rotational sensors are inbuilt into the motors, and we use them all the time, as you're going to see. So the rotational sensor of the motor is really important. And then the ultrasonic sensor or the distance sensor and the touch sensors, some teams use those, and those are all, again, left to your creativity on how you want to use them. And the gyro sensor is something really important because for the advanced coding that we are going to be talking about today, you'll see that we are going to be using the gyro sensor extensively. Now, I don't know how many of you have worked with the previous system, which was called the Mindstorm's EV3 brick. Now, Spike Prime has become the latest one for a couple of years at least now, but there may be members here who've used EV3. And the thing with EV3 was it had an external gyro sensor. And being external, it was not very reliable. There were times when it would just start spinning the robot around. Now, you don't have to worry about such things with Spike Prime. So if you've heard from others that, hey, the gyro sensor is not reliable, that it can go bad or it can make your robot simply start spinning, that was true with the older system, not with the Spike Prime. So please reset your thinking, or if you've had that advice, I would suggest giving up that part from your minds, because the new gyro sensor in the Spike Prime is really reliable. We have not had one instance where it misbehaved like the older gyro sensors. And regarding what is yaw, what is pitch, and what is roll, hopefully that image there provides you with an understanding of what kind of turning of your robot would be affected by each of those. Now, depending on when you built your robot, how you placed your brick, you'll be using one of those 3 angles extensively in this coding class. So if your brick is simply flat like this, then it is really the turning that you're going to be concerned about. And for turning, that's the yaw. So in our examples, you'll see that we're using the yaw angle for all our calculations. But if for some reason your robot has been built with the brick, the Spike Prime brick sideways, then please let us know, because accordingly you might have to use a different angle. You may have to use the roll or pitch depending on how you have put it sideways. So with that said, let's open up for the first round of questions, because we just gave you some information about basic hardware, and we want to see if any of the members have questions. So let's see, we have 4, 8, 12. We have about 14 members remote, and we have 4 members here in person right now. So does anyone have questions about the motors, the brick, or the angles that we use? So we're all coaches, just like your parents who coach, so don't hesitate. There's no teachers here, there's no principal here. Just like your parents who probably coach some of your FLL teams. I'm a parent similarly who's coaching the FRC team. So please feel free to ask us any questions.
Can a parent ask a question on behalf of the student?
Yes, thanks for asking that. Yes,
Yeah.
parents, if you're on, you're welcome to ask any questions. Please don't hold back.
Cool. So we have a total 5 sensors. You spent a bit of time to explain the gyro sensor. Could you briefly explain about the other 4 sensors also?
Sure, yes. So let's go back to the other sensors. So frankly, we've done FLL now for 7 seasons, including some of the students we're seeing here. They all did FLL as younger kids. And in our first year, we used the color sensor a bit, and we used the gyro sensor. We have never used the distance sensor or the force sensor in competition. But having said that, we have seen some teams that have used them. And the force sensor was used largely when teams used to back up into the edge of a table to straighten their robot. That was a technique that they used. Now, with the gyro sensor being reliable, we don't see many teams try to do that because they just rely on the gyro sensor retaining its angular knowledge through the whole game. But let's go ahead and discuss each one of them. So the distance sensor, this one, as far as being able to detect the distance to a specific mission, it's not really reliable for that purpose because of how the missions have, Lego parts which could you don't know which exact Lego part is being detected. So we have not really seen any teams that use the distance sensor to detect the distance from a mission model. But there have been teams we had seen in the past that would, there's this perimeter around the mat. So there would be teams which would use the distance sensor to detect how far they were from the edge of the mat by looking at the distance from one of those edges. And as with the Spike Prime, they have a range of about 200 centimeters. And then the force sensors, they're really touch sensors. So if you see this part here, when it's pressed in with a force of up to 10 newtons, it can actuate the sensor or trigger the sensor. And there were teams that would use a couple of those on the two edges of a robot on on the two ends of a single edge. And then it would back into one of those wall perimeters and use that to level itself. So that's one way we have seen force sensors being used. But again, having said that, our teams, when our students were FL members, we did not use either of those. Now the color sensor, that was a useful one. As you see, if any of the parents or students have gone and seen back at the previous year's FLL mats, there used to be a lot more black and white lines on the mat. That has increasingly, or I should say, that has decreased quite a bit at this point. Back then, when they did have a lot of those lines, it was popular to use a color sensor. So you would follow the black line all along to reach at least close to a specific mission model. Now, there always are creative ways in which you could be using the color sensors. The line following, though, has gotten tricky because, as you will see here, even in this year's archaeology mat, we don't really have too many of those black lines to follow. We have one there, and then one on the right-hand side. And I think that is actually, oh yeah, and then there's one here on this last mission model. So that kind of shows you how using the color sensor to follow lines may not necessarily be a very useful thing for this year. But having said that, it is definitely a really good exercise for the students to learn. It shows how you can use the color sensor. So what we would suggest is in the initial weeks when you're still learning, definitely it's a good one to figure out how to use. But for comp, it may have limited use. Again, like I've been saying, teams get really creative. So there may be ways in which they use the color sensor to reach a specific point on the mat. It could be detecting, just going on till you find the solid black line and then taking the next action. That's definitely one thing which can be done. And then let's see, rotation sensors. So those are inbuilt into the motor. They basically tell you how many times the motor has rotated. You can do that in degrees. You could do that in there's its own units which come in there, where a whole 360 is a unit of 100. So you could use that, and you could use distance after having given it. If this is mainly for movement motors, you have to provide the wheel circumference, and then you'll be able to use distance also. We tend to stick to degrees because that is easier for the students to work with. And then lastly, the gyro sensor, which we were talking about. So any more questions on that?
Thank you. Thanks.
I don't totally understand that. Rotational sensor.
So Bryce, sorry, you had a question about the distance sensor?
About the rotational sensor.
Oh, rotational sensor. Okay, all right. So when you're using motors, you want to know how much a motor has rotated. This is for both the purpose of moving the robot back and forth, and also for the purpose of moving attachments. Because if you don't know how much the motor is rotating, you won't be able to constantly get your robot to a specific spot or get your attachments to specific positions, right? So that's where you use the rotational sensors. And the way you use the rotational sensors, that's inbuilt in the blocks, where you can basically indicate, move this motor these many degrees. So if your command says move the motor 360 degrees, you'll see that the motor basically rotated one whole turn. And then if you say 180, it's going to be half a turn, and so on. So that's how you use the rotational sensors. And they are a key part. In fact, I would say the most important sensor on your robot is the rotational sensor. Because without using the other sensors, you could still try and solve some missions. But without the rotational sensor, you simply will find it really hard to solve most of the missions. Okay. Anyone else have any questions? Okay, all right. So with that, Zainab, if you can go ahead and get started with programming recap. You can introduce it.
Hi, my name is Zainab, and I'm going to be talking about programming. So there are 10 block sections in Spike programming: motors, which are the blocks to control the movement of the individual motors; the movement blocks to control the movement of the drive motors; light blocks that can control the light grid; sound blocks that control the speaker; event blocks that are wind blocks and broadcasting; control blocks, which are wait blocks, conditional blocks, and loops; sensors, blocks for reading data from sensors; operators, mathematical operations; variables, blocks for using variables that have been created; and my blocks, blocks that you can create yourself. And you can add there are 2 extensions that are necessary for the code that will be created in this camp. So there are 2 steps, and you have to click on the extension button in the bottom left of the screen and check the more motor and more movement extensions. This will help you get connected.
Okay, so at this point, I would request all of you to get your device, which you're going to be using for programming, out and open. So if you're going to be using a Windows, Mac, or Chromebook, please get those out. And if you're going to use an iPad, that should work also. Now with the iPad, let us verify this. We had intentionally requested laptops because we know that the extensions will be available for laptops. Whether it's available for iPad, we will know here shortly. But I think there was a season when iPads did not have extensions, but I think they changed that. Yeah. So what we would request is, and maybe we will go ahead and show you where exactly that would be. So if you guys can go over to the left-hand bottom corner here, you will see an icon.
Like blocks with a plus on it.
Yeah. It's at the left bottom corner from the shared screen. So that's what you would click. So guys, if we can make sure that all these students here, yeah, you can click it. Yep.
Oh, yeah, it does work on.
Then you click the more motors and more movement.
And also they can add more sensors.
You can do more sensors.
By the way, guys, the lens.
We didn't say what it's for though.
Right. Okay. So let's jump into exactly why we are doing this. Right. So as you will see, when in the default installation, there are a few blocks available for working with motors and working with movement motors. But adding these extensions gives you access to a few more blocks, which give you extra capability. And for using some of the advanced algorithms, we want you to have that capability. That's why we want you to add these extensions. So let's go back to, so please go ahead and add this, guys. So let's make sure. Yeah, so if you can all open up the Spike Prime app. For the students who are here locally, let's make sure you all have the extensions added.
So should we first create a project and then go to extensions?
So yes, because you would need to be in the user interface, which allows you to access the blocks. So yes, please. Yeah, that's a good question. And so what we would request is when you start your app, you're going to be in this screen. So please click on new project, and that will give you access to this interface without the code, of course. And then if you scroll down to the bottom or look at the bottom left corner, that's where you will see that icon, show block extensions. So please click that. And then you can select more motors, more movement. And if you are trying to play around with more sensor stuff, you could select more sensors as well. And then, of course, the others are fun as well. But from an FLL perspective, I think it's really these three which you would primarily use.
And more movement and more motors. So these three.
So everyone who's here in person, do you all have your extensions enabled? And iPad, that works as well?
Yeah.
Okay, perfect. All right.
That's it. That's it.
Just read.
So just checking with everyone, please confirm if you have been able to get the extensions enabled. Okay. So just giving a few more seconds. If anyone still needs time, please let us know. Otherwise, in 10 seconds, we will move on to the next part. Okay, all right.
Hi, my name is Naman, and I'll be covering turning with gyros. So basically, when you use a gyro turn, you basically just use your gyro to turn your robot. So we'll be going over the basic gyro turn. I just open this.
You can go to the slide.
Okay. So what we'll do is we'll make a my block and take a target angle input. And what this will do is we'll set it to set our yaw angle to 0, which will reset our robot's angle first. And then after setting our movement motors and some of our motor settings, we'll set our target angle to our target angle -5. And we basically do this so we have sort of like a, what do you call it? Like a,
It'll overshoot.
yeah, it won't overshoot. Yeah. Yeah. So you have a little bit of variance what you can use. Then we'll start moving both of our motors with our left motor at 20%, our right motor at negative 20%. And we'll wait until our yaw angle is either greater than or equal to the angle we wanted to start at, and then we'll stop moving.
So let's just talk about a few more details in here. Firstly, we want to make sure that all of you have used my blocks in the past. And is there anyone here who has not used my blocks? Please let us know. So when there's a piece of code or a piece of logic that you want to reuse again and again, that's when my blocks are really helpful, because you are creating it. As you will figure out later on, when in programming, there's something called methods, and this is our functions, and this is really a similar concept wherein you're able to reuse that piece of code multiple times, because in your whole program, you might be turning up, many times. You don't want to have to repeat all that code every time you need to make a turn, and that's when you use a my block. And in this case, the my block is called basic gyro turn right. So whenever you need to turn right, you would use this block. And then it takes a variable value, and that is your target angle, because you may be turning a different amount of degrees each time. And that's why it's a variable which you provide, and then it will turn accordingly. And now, having said that, it is important that you understand every line of or every block here. There's a reason we have every single block in here. So firstly, setting the yaw angle to 0 at the beginning of the program. Can someone guess why are we doing that? Does someone know why we are setting the yaw angle to 0 at the beginning of the program or beginning of the turn?
I think Bryce raised his hand.
Because
Yeah, go ahead, Bryce.
because you have to first set your robot, and then you have to. It depends about the angle.
Right. Because if you do not do that, you do not know at what angle you're starting. And if you don't know at what angle you're starting, how much are you going to turn, right? So you always want to treat that as, okay, this is where I'm starting, and now I'm at 0. That's how you want to start every turn. And then the next one was setting movement motors. So we had indicated how important that is. Please make sure that you're setting the movement motors. Now, in this case, we're setting it in the my block. Now, it's not wrong if you set it at the beginning of your program and you don't have it in your turn my blocks. That's okay. So you guys can decide what you're comfortable with. But then there's the expectation that whoever writes a program and uses the my block knows that they have to set the movement motors at the beginning of that program. Okay. So you do want to try and avoid having actions within the my block which need to be done only once, because you could do it at the beginning of the program once and you don't really need to keep doing it again and again. But in this one, because we want to talk about each of these important settings or blocks, we have this in here. And then set movement motors to brake mode at stop. So I hope everyone knows this, but when you have two movement motors set on the robot, there are modes in which you can have them working. So when you have it set to brake mode, what that means is when it reaches the target, it's just going to stop right there. Like at the end of that block, it's going to stop right there. Now, can someone tell me an example of where you don't want that behavior, where you don't want it to suddenly stop? Okay. They're wanting to push something. Yes, kind of, yes. So the one of the answers here was when you want to push something. So what that basically means is you're not intending to stop at that spot. You do intend to continue moving, maybe at a different speed, because now you're pushing something. You don't want to be pushing it at the same speed that you reached that location, right? So when you want to be a little slower, you don't want to stop and then again reach a slower speed. Instead, you just want to transition from a faster speed to a slower speed without that sudden break. And in fact, that makes for more reliable behavior if you're not stopping suddenly for no reason in between your whole path. And that is why we set it to brake mode. Well, in this case, it's being set to brake mode, but When you know that you're not stopping, you're going to be continuing your movement. In that case, you will not set it to brake mode. Instead, you will set it to a mode which will allow it to continue moving. But please remember, the rotational sensor will indicate that, hey, I'm done with my 480 degrees of motion. And then the next block will take over immediately from that point. That transition is so quick, you don't have to worry that you have moved some extra degrees. It'll instantly go into that. But what we get here is it's not going to suddenly stop and then start the next block. Instead, it will smoothly decelerate if you're decelerating, and then it'll accelerate if your next block is going to make it go faster. So some of these questions, if you want to discuss, please keep it in mind. We can talk about it during lunch. Any general questions you may have like that, or even after the whole session is done. But just wanted to indicate some of those things. And then set movement acceleration to slow. So why would we want to start accelerating slowly and not just go like a race car, just start off at high speed? Anyone want to take a guess? Yeah. Exactly, unreliable. Because remember, whether it's a regular robot you're building or whether it's FLL missions you're trying to solve, reliability is important. You want to be able to repeat your success every time. That's what makes your robot precise. All the top teams, they have robots that are precise. And in order to get that reliability, you need to pay attention to these little things. So if you're going to start accelerating like a race car, true, you might actually save a few seconds. But what you will see is there could be slipping happening. So your wheels might rotate in the same spot. You might have seen, I don't know how many of you are car fans, but you guys have seen when cars accelerate suddenly, the wheels will spin on the spot. And when it does that, what's happening is your motor thinks it has rotated that much, but you have not actually moved. And that decreases your reliability. Now, there are some other ways in which we might be able to, yeah, go ahead.
Like when you're like, if you ever have a chance to like slip or anything, isn't that where you can use yaw?
Sorry, could you repeat that question? It was kind of quiet.
Yeah, like if you ever slip or if any faults comes in your like robot when you're activating it, isn't that a place where you can use yaw?
Yeah, you could do that, but we found that it's like more precise if you start off like with your move acceleration to slow, especially when you're testing, and you can just tune it more and more depending on your specific robot. The question was like,
Okay.
if you're using your yaw, why does it matter that you slip?
Oh, wait, so we're not necessarily talking only about turn, right? In fact, that is also one possibility where your robot might end up rotating a little left or right because you accelerated so suddenly. But that's not the only concern. And you're right, that concern will be addressed because we use the gyro turn. So it's going to straighten itself back. But the other concern is if both wheels slip the same amount, or if one has slipped a little more than the other, in both cases, the rotational sensor thinks that the robot has moved a certain distance, but it actually has not because the spinning happened on the spot, right? Because I'm sure, if you've solved missions before, you probably measure the distance and then, or maybe you have that little marker on the side of the wheel and you have your robot pushed so that you know how many rotations and hence how many degrees you want it to turn to get to the next mission. But if it's spun in the same spot, it will think that it has already moved that much. So when it finally stops, it will stop a little too far away from its intended location. Does that make sense?
Yeah.
Okay.
Yeah.
Right. So yeah, definitely, find the sweet spot for where the acceleration should be medium, where it should be slow. And there may be some times when it's okay to have it fast. For example, when you're starting slow and then you want to maybe send the robot off to the other end because you have two drivers on one side and two drivers on the other side. So maybe you are simply sending the robot from one set of drivers to the other set of drivers. In that case, you really, as long as the direction is correct, it doesn't matter if it, stopped a centimeter or two far or too close. In that case, yes, you can have 100% acceleration because you want to quickly give it to the other two drivers. So that's why think through and apply these different options based on what you think will apply for the situation. Okay, anybody have any questions regarding all these things we spoke about? The movement motors, the brake mode, and the acceleration mode. Okay, and then the rest of what you see there is basically related to how you would turn. So what we would request now is if all of you can please go ahead and in your project, go ahead and implement this turn. And if you have a local robot with you, like if you have your own Spike Prime robot with you, you can run that. And then for those who are here, if you have your robot, you can run that on the mat here. Otherwise, we'll run the demo robot and show this in action. Okay, so at this point, the request is please go ahead and implement this code. You can look at what you see here and get that on your project. The code is documented?
Yeah.
Okay, can you run it?
Oh, you meant project like that. You just
Can you do it?
okay. Ready a file. This is the file. It's just this one. So that's short for that. How do I get to the
Can you show us the other pictures?
Was that a question or?
oh wait. Oh, there's screen as well. We're just recording now. Still recording. Still recording. Yeah.
Done?
And wait, did any of you guys have like a robot?
Did you bring a robot?
yes,
Want to try out
robot.
here?
I have a braid, but you don't have.
Okay.
Oh, that's fine. You guys can test it out.
Oh, yeah. If you guys want to connect to this one and test it, feel free to do that. We'll maybe run it once here so that you can see it. Yeah, so you guys
Did
saw
you-
how it turned.
Did you get the
So
code?
it's making this turn right now.
You see it turns right. And it is a little bit off, so we can actually tune that value. So
Wait, this is just for it.
yeah, that's fine. All right, I'll wait. We'll
Oh,
wait till
they're
you
not
guys-
able to see it properly. Okay. Hold on.
Yeah,
So,
online they can
yeah,
see it.
yeah, let's do this. Let's,
The screen
Sure.
sharing is paused.
Feature paused.
why?
Because they
People on
can
the
see
screen could see it. The-
Oh, can we go ahead and expand this one
Yeah, sure.
and show this one?
yeah, I guess, yeah.
So guys, you should be able to, can you? So guys, I think on the presentation, it was probably not large enough to see easily, so hopefully this helps. Please let us know if you're able to see this now. So for those who are here in person, maybe now you can see it from your spot.
And also, if you guys like, are confused, like, like what some block is, you just have to, like, you can ask me or not.
Right, for those who are on Zoom, if you have any questions about any of these blocks, please ask us now.
Yeah, and you can either put your questions in the chat or just like speak
Yeah.
aloud.
Is there anyone here who has not worked with variables before? Anyone on Zoom who has not worked with variables before?
You want to ask about the first word?
I have a question. Like for your first block that you used, what does it do and how do you get that block?
So by the first one, do you mean this red defined that block?
Yeah.
Okay, so that is my block, and the way you get my blocks is you have to click on this category of blocks called my block over here, and then you will get to this screen. And if you have never created one, you will not see any of these red options here. You will simply see make a block as the only option. So that's when you would click on it, and when you click on it, you're going to get a make a block dialog, and in the block name, you give it a name. In this case, it was, I think,
Like
gyro turn right or something like that. Yeah. So you will give it a name that corresponds to what your my block is going to do. And then in our case, we need an angle, right? Because the my block needs to know how much to turn, which means it needs to be given a value, and that is the input. So we need one input for this my block, which is the angle. And that's where, depending on whether it's a Boolean or a number or text, you would click on this, and that will automatically, like you can see here, when you click on it, it will add a variable here, number or
Yeah.
text.
And in
Then-
this case, we need a number of text, not a
In
boolean.
this case, we need a number or text. So you'll basically do this, and then let's actually give it a sample name. So the turn right, gyro, turn right, and then for number or text, you can give a name. Okay, angle. So that would be the name of your variable, which needs to be given to that my block. And then you hit save, you will see that you now have these options available. I'm going to not save this. I'm going to delete this. But then when you do that, then you will see that a couple of these options become available to you.
Yeah, and also the like define block here, it'll just pop up in your workspace.
Yeah. So once everyone has this part done, please let us know. Yes. Well, not the looping logic. Maybe.
Oh, yeah.
Yeah, let's go through the looping logic. Once they all indicate that they have this on.
Same for this one.
For this one. Can you guys check chat, see if anyone has questions?
Robot turned 45 to 90 degrees, right? Where did it pull the target angle from? It is not.
So you guys feel free to send me this one and run. If you want.
Okay. So
That's
wait, I'll explain that. So yeah, this is the actual like my block, right? But the way you actually use it is here. So in your when program starts, like in the my block section, you basically just drag it out. And then this input is our target angle. So this is the code we ran like when we showed it on the video. So you just input 90. So that means that you want to turn 90 degrees to the right. And yeah, that's how you actually use the block. So like that 90 is basically being plugged in here to target angle.
To make it turn both ways, can we just put a boolean in the that moving?
I'm sorry, what did you say? Can you repeat that, please?
To make it turn like right and left, couldn't we put around the start moving? We could put a boolean, like an if else or to if.
Oh, yeah, if you want to do that, yes, that is possible. In this case, like he was suggesting, instead of using a separate one for right and separate one for left, you could use an if else block.
Oh
yeah.
yeah, this
Yeah.
so this is like just a very basic program just to like get you guys to understand how the gyro sensor works. But our next program like will do that. Yeah.
I think Shreya.
Yes.
Sorry,
Um,
Shreya
yeah.
raised
Oh
up.
yeah, you can go ahead. If you had a question.
How do you get the set target angle thingy?
Yeah, target. Oh yeah. Okay. So
You mean like the set block or like how you?
Yeah, no, that's a good question. We need to add a variable. So please walk through that. So there was a question on how this target angle showed up here, right? So that's where using variables is needed to do that. And let's actually go
Yeah.
through and show them how to use a variable.
Okay, yeah. So if you go into like the variables tab here, you'll see that you might already have some variables, but if you don't, what you would do is you see a box here that says make a variable. So in this case, you just make and you just call it whatever you want. So we called ours target angle, and that makes it simpler. But you can call yours whatever you really want. And then you take this and you would drag a set block. So in this case, we use set and we change that to target angle. And then we added a minus and then target angle -5, just so we have a little bit of variance for overshoot. Does that answer your question or?
Yeah, thanks.
Cool.
And if you're all observing the video, for those who are done putting the code together, if you're observing the video, this is the robot is making 90-degree turns and stopping for a second and then turning again. But if you observe, it is not always perfect 90,
it's really inaccurate.
right? It is actually going on turning a little more than 90 every time. So if you keep watching, after 4 turns, you'll see that it's actually gone beyond one whole circle.
Yeah,
Because 360,
yeah, we can see it's like overshooting or like between 5 and 8 degrees every time.
oh yeah, so can you guys go ahead and talk about that screen which you're showing right now? Because everyone may not be
yeah.
aware of that.
Yeah, so this screen, it's really useful. It basically gives you like data on like stuff like your motors and also your gyro data. So here we're just looking at the yaw. So you can see it's like resetting the yaw to 0 and then it starts turning until it hits 90. But the thing is, because it's moving so fast, the like when it stops, it tends to just overshoot even with the motors on brake mode. So that's kind of what this
Can you go
part
back
over
to that
here was.
screen? And
Yeah.
as you can see, it does not always overshoot the exact same number. Sometimes it's 3, sometimes it's 4, and I even saw 9 and 8, which means it becomes hard to have a compensation, a fixed compensation, when you do this. And also, depending on how many degrees you're turning, the overshoot is going to be accordingly different also. And that is why we now will be, after this, we'll be looking into how to address this issue.
So because we see it's like overshooting generally from like 4 to 9, we can try and adjust this value a little bit. So we can add like 6 is kind of in the middle of that. Yeah, 11. Right. Yeah. So um, now we change that value. So we're gonna run it again and see if it's a bit better. Wait. Yeah. So now it's looking like a lot better. But we're still gonna see like some inconsistencies.
Now it's not turning down.
Yeah, so now it's like, yeah, so now it's going between like 88, like 92, like, so it's still inconsistent, but we adjusted it a little bit.
So what we've seen is some of the newer teams, when they start off using the gyro sensor, they use that compensation number to try and make it improved. But that, again, as you see, does not really cut it, right? It still is going to be a bit inaccurate. And when you're going through several missions in one run, all these angular errors are going to add up, and you want to avoid that. And if you want, the top teams, they try to be as precise as possible. So next, let us see what kind of algorithm or mechanism we use to overcome this issue where there's undershooting or overshooting happening.
Right, so really quick, has everybody finished copying down like the code? Is there anyone who hasn't finished copying it down? All right, and also, anyone online, are you guys like, do you guys have a robot with you, like that's ready to run? Or are you guys like just on your laptop? So, all right, so it doesn't look like anyone has a robot that they're running on. Oh, you do? Okay. Did you test out the code? Yes, like you tested, did it like work fine? Okay, all right, that's good. All right. Yeah, so I think, all right, in that case, we're ready to move on. Okay.
So the next step of after our standard gyro turn is our P control gyro turn. So P control or decelerating turn uses.
Bryce has a hand up.
I think that was for the
Yeah, it
previous
is.
thing.
Oh.
Yeah. Yeah. So this uses the gyro to slow the turning speed as the error or how close you are to your target angle reduces by using a proportional algorithm. So in this case, speed is proportional to error. The error is how many degrees away from the target angle the robot is. So we calculate this by doing error is equal to the target angle minus your current angle. So at first, we'll set the error to the target angle because our robot hasn't moved yet. And then we'll use a proportional algorithm, which is speed times our constant times the error, or speed is equal to our constant times the error, to calculate the speed. So in this case, we're using 0.5, but this will need to be tuned for your robot. So we also, in this case, we do clamp, which is basically if our speed is lower than 5, we'll set it to 5 just so that our robot doesn't slowly try to move, but doesn't end up actually moving because of friction. Let's go ahead and start building this.
Also, wait, really good. That was smart. I'll explain this. Yes. Yeah, so like just an easy way to think about like what the P control algorithm is. So if you guys have like learned about ratios in school, you can kind of think of it like you're saying, so here our constant is 0.5, right? So what we're saying is our speed is like it's like a 1 to 2 relationship with our error. So like if our error say is 10 degrees, it means the speed we're going to be moving at is 5%. And if our error is say like 90 degrees, it means our speed is going to be 45%. So that means like as your error is getting lower and lower, your speed is going to also get lower and lower. So that's going to cause the robot to decelerate.
And one thing to clarify there is the term error, right? Now, error here really means how many degrees of turn are remaining. That's what it really means. It doesn't mean there was a problem and there was an error, right? The reason it's being called that way is that's how much turn is left before it reaches its target, before it reaches its state of completing what it's trying to do. And that's why it's being called error. But feel free not to use the word error if you don't want to, if you feel it's confusing. Instead of error, you can use the term remaining angle, because that's how much is remaining on the turn. Okay.
So we can go to our my blocks and we can make a block. We'll call this our P control turn. And the same way we did for our previous thing, we have to add an input. And we'll call this our target angle. We can just go ahead and create this. So this made a define block automatically. And similar to the way we did it previously, we can go ahead and set our yaw to 0. here. And follow the same thing we did for our movement motors. So we'll set our movement motors to A and E. And we'll set our motor to brake mode. Brake as stop and stop. So this is the same thing we did previously as well. And in our variables, we will set our error to 0. As Coach Tree said, you can call this like remaining or anything like that, whatever is easiest for you. So we already have the error variable created, so we'll just drag that in here and we'll set our error to 0. Okay. And now we will do a repeat until block. And here we will check if we still need to keep moving. So we'll add an or. And then we'll do to the value of our error. And we'll set this to 2. Can anyone guess like why we're using absolute value here?
That way, if it's a negative number, it will always be counted as correct.
Exactly, yeah. So even if it's negative, we still will want to keep moving. And we'll do the same thing for this one. Why do you guys think it would be negative? Like when would the error be negative? Anyone in person? No?
In turn where you want to turn left.
Yeah, if you want to turn left, then it'll be negative.
Yeah, that. And also if your robot's moving too fast and you overshoot, in that case your error will also be negative. So yeah, both those cases. So let's just
I'm zooming in.
yeah.
Like the code that you're making, what does it do?
This is like the P control gyro turn. So after our basic gyro turn, this will use like an algorithm to make it even more accurate than our previous method.
So basically
Okay.
what's being there are a couple of things to be aware of on how we're doing this, right? So in the regular gyro turn, what you did was you had a target angle and you kept turning at a certain speed till you reached that target angle. And if you overshot it, well, it treated it as I've already reached it and it would just stop. Now in this one, there's some control here. And that P control basically means depending on how many degrees of turn are remaining, it will vary the speed. So if you have a large amount of turn left, it's going to turn faster. And as you get closer to your target angle, like the intended angle, it's going to start slowing down. That's why it is called proportional control. So the speed at which it turns is proportional to how many degrees of turn are remaining. Because when you have a 360-degree turn, you don't want to do the whole 360-degree turn slowly. You're going to be losing time. You want to turn as fast as possible initially. But then when you start getting close to where you know you're going to have to stop, you want to be slower at that point. That's why it's proportional to the number of degrees remaining. That's one thing. And then so the nice thing about this is when you have 2 or 3 degrees of turn left, that's where that clamp of 5 degrees or 5 was shown to you. Because if you try to move at such a slow speed of 1 or 2 times the power, it's not even going to move the robot. So we move with at least a speed of 5 times the power. And when you do that, there'll be slow turning going on for those last 5 degrees. And it is usually slow enough that it does not overshoot. But if it does overshoot, then it detects the negative error and it'll actually go backwards. So in fact, when it's turning, if you intentionally push it and make it turn more, you will see that it'll turn back to where you had originally intended for it to stop. Does that explain what we're doing with P control turn versus the regular gyro turn?
What
Yeah.
movement acceleration constraint?
Sorry, I think there was another question. Can you please repeat that?
What is the the set the acceleration speed?
Set movement acceleration. Are you asking about this one? Hey, Bryce, are you asking about
Yeah.
set movement acceleration?
Yes.
Yes. Okay. So like we explained a little earlier, what that does is when you are going to start your movement, it won't, let's say for example, in this turn, right? Let's say you're going to take a 360-degree turn. Now the power at the beginning of that turn is probably going to be maximum power. You don't want to suddenly start turning at the maximum speed. You want to kind of accelerate slowly into that max speed. That's why we set it to movement acceleration to slow. Like how we discussed earlier, this is so that we avoid wheel slip, so that we don't have the wheels spinning in the same spot. Now, in this case, because it is just a turn, true, you would probably finally end up at the exact angle that you intend, but you don't want that slip to move your robot in some other direction, even a tiny bit. Again, for the sake of precision, you take care of these little things. Okay?
Huh?
Anyone else have any other questions before we continue? Okay.
So inside of a repeat until block, we can now go ahead and set our error to our angle. We'll drag our target angle here, and then we will do minus our so what this will do is this will set our error to like the amount that's remaining. So by doing our target angle minus the angle that our robot's currently at, we'll know exactly how many more degrees you have to keep turning. And then we can go and set our speed. At this point, you'll probably have to make the speed variable as well, but we already have it, so we'll just keep going. And we'll set our speed to.
Should we wait for them to maybe create the speed variable?
Sure, yeah. So go ahead and make your speed variable. Okay. All right, and then we can just now set our speed to our error times 0.5. This was the ratio that like Rahul explained to you, our 1-to-2 ratio. Now we can work on the clamps that we did. So we can check if our speed is greater than, and then we'll add our speed. If our speed is greater than 0 and the same time it's back. And 5. So this is the clamp, as we were mentioning earlier. So if our speed is less than 5, which might make your robot not move at all because of the weight and friction, we'll just set it to 5 so that we're actually moving. Then we'll do the same thing for the other side as well.
So I have a question. So, like I see in your code, like previously, you did set error to 0. I like the first under the set movement um correlation to slow.
Yeah.
So like can you actually kind of just like review I can you just say how you did this one more time again?
Yeah, so what you would do is you'd go into your variables and drag your set block and set your error to 0. And the reason
I was doing this, it's supposed to be set to targeting.
Cool. Yeah, in this slide, it's.
Okay.
I
So,
realized it in my-
yeah, that was actually a mistake on our part. Sorry about that. Thank you for catching that though. So we set our error to our target angle because like it's the remaining amount that you have to go. So before you move, you still have to go all the way to your target angle. Does that make more sense? Or
Okay,
yeah.
that's good.
Now we can keep setting our. Yeah, and then we set the same clamp on the negative side as we did on the positive side as well. And now that we have all of our calculations done for our speed, we can start moving at that speed. So we'll do start moving at and we'll set this so we'll move one motor at our speed and the other motor at the negative of that speed. And we'll get that by multiplying by -1. We'll just move
I
this
have
thing.
another question about like the same thing. So about like the set error to target angle. So when I go to my variables on my screen, it doesn't like give me it just says make a variable, and I kind of need help with like making that. It's like
Yeah, sure. So you would just go, you see like a box that says make a variable. So you just click it and you'll see something like this. So you can name this like whatever you want. It could be easier if you name it error, but we'll just name it like remaining angle or something. And once you hit OK, you will find it right here and you can drag it out and use it. Or you can drag out the set block. So the set, and then you would choose the variable you want to rename here. Does that make sense?
I can't really like find the set block. Like, can I do it?
There, right?
So did you click make a variable?
1 second.
Yeah, just
Okay,
like
yeah, I got it.
you
I
got
got
it.
Okay, cool. So on our code now, we started moving, and our repeat until block will keep moving until we're within our bounds, so like 2. And then now what we can do is once we're done with all that, we can just tell our robot to stop moving. Yeah, so that's the P control turn. Let us know if you have any questions, and then just copy this down. If you have a robot, feel free to test. And people in person can also test here.
Can I have a question? So how
Yeah, sure.
the set movement motors to brake and stop?
Mhm.
And then so why do we need that line? And since we already say that stop moving in the end.
That's a good question. So stop moving, all it'll do is it'll stop sending power to the motors. But if you don't set your movement motors to brake at stop, your robot could still keep moving just based on its own momentum. So by setting movement motors to brake, it'll basically make sure when you tell it to stop moving, it'll actually just physically stop all the wheels and make sure they can move. Does that make sense? Or
Yes, sort of. Thank you. Yeah. So So if so this is mainly for that, like the accuracy, like
Yes,
because of
exactly.
the momentum and the speed that would overshoot the turning angle and stuff.
Yeah.
Okay,
Yeah. So
got
once
it.
you move, like get to the stop moving, at that point, if your robot keeps overshooting, the code can't correct itself. So that's why we do that for accuracy.
Okay, thank you.
I have
I see someone's raised their hand. Does anyone have a question?
Yes. My question is, what does the code inside the repeat until really do? Like, what does it really mean?
Yeah. So what it's doing is every time, like it'll keep repeating this, like at a certain time, and what it'll do is it'll keep checking if you're inside like our bounds, which are if our error is within 2 or is equal to 2. So it'll keep repeating that and keep changing the error and the speed until that point, which is the point of like the decelerating turn.
Okay, thank you.
I tried the program and it near the end it kind of feels like glitchy kind of my robot.
Sorry, Bryce, could you repeat that?
So when I run the program, I kind of feel my robot like it feels like glitchy when it finishes turning. It goes like it has closer to me.
Sorry, it's like hard to understand what that last part was. Would you mind like sending it in chat? I think your mic might be like distorting the audio. Yeah. But also really quick, has anyone not finished copying down the entire program? All right, so I'm assuming then in that case, everyone's finished. Oh wait, on you should you have a question?
He's not done yet.
He's not. Oh wait, sorry. We have one person in person not done yet. Wait, on Yusha, did you have a question?
No.
Oh, okay. Yeah, your hand was just. Um, okay, so we're gonna, if you look at our video, we're gonna basically run this program. Also, do you want to just put it up there? Make sure it has. Hmm? Yes. That's it. Turn Bluetooth. Hold the Bluetooth button. Yeah. Okay. Oh yeah, so we're now gonna run it. Yeah, you guys can see the turn is much more accurate. And you guys can also see how the robot at the end it slows down a lot. So like it starts off really fast and then it slows down. So that makes the turn really accurate.
And we have to open up the screen again, and you can
Yeah.
see that our yaw is going to be
Yeah,
90,
perfect 90.
perfect 90 every single time.
So this is like gonna be like at least when I was doing FLL, this was like pretty game changing. This like algorithm because it allowed our consistency to be like a lot higher.
But wrong.
Yeah.
Go back to.
Oh yeah, I'm not there. It's like
And then put the stop. I can switch back to the part.
Is anyone having any issues with running it, or is it working for everyone?
Yes, I think so.
Yeah.
Near the end of my turn, robot speeds up and then stops. Speeds up and then stops. Huh. That's
Could you please go back to your code again? Thank you.
So Bryce, just like maybe double check that all the code is like the exact same as this. And then yeah, if you just let us know if you see any like differences.
And make sure you're running your P controller, not your old code by accident.
Yeah. And also, if you look at the video, after like probably like 25, 30 turns, we have like only a little bit of error. So that's like really good, considering that in one of your runs, you're probably gonna be making like less than 10 turns. And so, yeah, it's pretty accurate. We go on to the finish.
Yeah.
Also, if any of you guys want to, you guys can like text the program on this.
Yeah, feel free to,
Yeah.
you can connect to this, download your program and run.
Yeah, so there's who wants like you want to do it? You know. And yeah, you guys can help it. So.
Bryce, were you able to fix your issue? Okay, good.
Yeah, I think you just put on time. You put it in. So, you want to try turning left for like maybe. We haven't shown any left wings yet. So you can see the program works just the same for turning left or right. All right, who else wants to drive?
What the movie story?
Oh, we're getting to that next. Don't worry.
Because if it's your turning, then it can't go and
Yeah, so we started with the turn because it's like a little bit simpler to understand like the logic, but we're going into the straight.
So once you're done with this, we'll have a short 15-minute lunch break or snack break, and then we'll ready to go straight.
put it straight.
Not exactly. It is.
Yeah, go ahead with your question if you have one.
Yeah, about your like code thingy. It says error. Can you just like double check? I just want to double check what is error.
Yeah, so error is like the term that's used, but it's the easier way to think of it is like the amount of degrees remaining between where your robot currently is.
Rename.
Yeah, it's like you can think of it sort of like the remaining angle. So we can actually like mention that here.
Yeah, did you want to talk about
rename it? So I think for simplicity, we can just call it like remaining. We can just rename this to like remaining. So it's just the amount of degrees that's between your current position to like where you want to go eventually.
Because remember, as you're turning, this remaining angle starts decreasing. right? Because you're getting closer to your intended angle. And at some point you get to 0, that's when you have reached your intended angle. So that's why you're constantly calculating your remaining angle as you're continuing to turn.
Okay.
If you're trying to turn left, would the program like the repeat until Boolean logic work?
Oh yeah, so for turning left, all this logic will work the same.
Yeah.
Yeah, because we have absolute value here. And then also for our minimum speed bounds, we also account for like if your speed is -5. So the way you would turn left is instead of doing 90 degrees, because in FLO with the gyro sensor, like a positive angle means you're turning right. So you would just put in -90, and that would cause you to turn 90 degrees left. Okay, so everyone like with a robot online, did you guys like get a chance to test this yet? And oh yeah, Bryce,
Yeah, he
were you
fixed
able
it.
to fix it?
Yeah, he said he fixed it.
So yeah, everyone with a robot, or is there anyone who has a robot who hasn't gotten the chance to test it yet?
For some reason, it was connected to my headphones instead of the Bluetooth or the microphone.
Oh, okay,
Yeah.
yeah, you
sound a lot
sound a
clearer
lot
now.
more clear.
Yeah.
Can you hear me now?
Yeah,
we
we
can.
can hear you fine.
So for the speed, the negative and positive number actually is the left or right.
Yeah.
Yeah.
So putting
Mhm.
so this like number here, that's like the angle you want to turn. Like so, -90 means you're turning 90 degrees left, and then +90 is 90 degrees right, rather than it being like the speed.
Yes. But here also for the speed, I also see like a 5 and -5.
Oh yeah.
Yeah.
So,
Yeah.
so
So it's like the same thing like the clamp. So if your speed is going to be lower than 5, which is if you're turning right, or lower than -5, which is when you're turning left. So that's just to account for like both
Oh.
possibilities of right and left turns.
okay. Okay. So even for the speed here, it means left or right.
Yes.
Yeah.
But I'm gonna listen and they're still talking.
Yeah. Is there anyone who's not
Is
ready to
your
move on? Oh yeah. Bryce, I think you might still be unmuted.
Yeah.
You mind just like muting?
So at this point, for everyone attending remotely, I think we will start our 15-minute break. And you don't have to take the break. We'll keep talking and things like that. And we may actually use this opportunity. Yeah. Yeah, sure. So yeah, even for the people who are here, we are starting our break right now. So for the next 15 minutes, if you have something you want to catch up and finish, please do that. If you have questions you want to ask us, feel free to go ahead and ask those questions to us. And also, I think we'll ask the people who are here in person to introduce yourselves. Just tell us your name and if you're already on an FLL team, which that FLL team is, and what your target is for this year, like what you're planning to do for this year. Okay, so with that, we'll start introductions here. For those who are continuing to code, please continue to code, that's fine. But we just want to start with introductions. Can we start from the left here? Do you want to go ahead, tell us your name, which team you're on? If you don't yet have a team, like if you're going to join a specific school and then start your team there, you can let us know that. Okay, guys, like, can we have silence? And then, yeah, sorry. Charles, you said you're Charles? You're planning to get a team soon. Awesome. So you'll be on another different team now? Same team again? Ah, okay. Which is it? Oh, Funky Fractions. Yep. BLMS team. Okay, that's Beaver Lake Middle School. All right. Okay. It's just mute everybody. Okay. You can introduce yourself.
I'm Daniel. I'm also going to be on one of North Shores Robotics.
Okay, North Shores Robotics. Do they have a name already? Those
Yeah,
teams?
Roaring Robotics.
Foreign Robotics?
Roaring Robotics.
Roaring Robot. Oh, right. Roaring
Each
Robotics.
team just has a different yeah.
Ah, okay. Okay, nice. Okay, I'm glad you're here, and hope you guys are getting what you want out of the camp so far. Yeah, please feel free to go ahead and start your snack or lunch. And then for those who are here remotely, do you guys want to introduce yourselves? Whoever wants can just go unmute yourself, and you can tell us your name and what team you're on.
My name is Shreya, and I'm on Dynamic Dolphins team.
Nice.
My name's Arvi, and I'm also on Dynamic Dolphins, and my friend and
My name is Anusha. I'm also on Dynamic Dolphins.
Nice. Okay. Are you guys getting what you...
I'm Alicia.
Yeah, sorry, go ahead, Alicia.
I'm Alishka, and I'm also in Dynamic Dolphins.
Okay.
And also another thing, can you please go back to your code?
Sure. Yeah.
I'm Vibhuti. I'm on G-Force, Team G-Force.
Okay. Others, if you want, you can introduce yourselves. So are you guys kind of getting what you were hoping from this camp? Is there, and again, we have a lot of experienced FLL team members here. I have been an FLL coach multiple years. So feel free to ask us any questions. And if there are parents out there, any question, you don't have to constrain it to just advanced FLL coding. So anything related to FLL, we'll be happy to talk to you guys. Is there anyone here who has not done FLL in the past at all? I have one person here in person. Anyone else who has not done FLL till now? Okay, sounds like everyone's done this before. That's good. Again,
on your screen,
yeah.
On your screen, I can't see your code. Oh, I got it. I got it.
You got it? Okay. Yeah, please take the next few minutes to grab your snack, take a break. I'm going to pause the recording for a few minutes.
Use operators to figure.
Okay, so I think the question was, is this way of turning more accurate? Yeah, go ahead.
Then absolute turning.
Right, is this more accurate than the previous turn? Okay.
Wait, so wait, when you say-
Then
Then absolute turning, where instead of resetting the yaw angle every time, we use operators to figure out and variables as the yaw angle instead of resetting the yaw angle.
Yeah, I think I get what you mean. Yeah, so actually using like absolute turning is more accurate because say you do like a 90-degree turn and it's off by like 1 degree, and say now you gotta like turn 90 degrees again, right? The thing with absolute like inputs is it's like a little bit more complicated because you kind of need to keep track of your like current angle. So it's not as simple as saying I want to turn 90 degrees and putting 90 in. You have to like say an exact angle you need to turn to.
Okay, let's go out. You want to sit here or outside?
I think somebody has like background noise on. Okay, I'm just gonna mute everybody really quick just to get rid of background noise. Yeah. All right. So the thing is, absolute turning is a bit more accurate because say you turn 90 degrees and it's off by like 1 degree, right? So like, see now you're at 91 degrees, and then now say you need to turn 90 degrees again, right? So that would mean that your absolute like value that you're turning to is 180 degrees. So you could like potentially correct that 1 degree error from before. The thing is, just for the purposes of this camp, to like make things a little bit simpler, we're just resetting the yaw angle. But that is sort of like a next step towards even more reliability, where you don't reset the yaw angle. You basically keep track of it like throughout your whole mission. So yeah, that is also like a valid and slightly more accurate way. We just have it this way, like to simplify the program, like for all of you guys.
And that could still be done with using this my block. But
Yeah,
keeping
yeah.
track of the angles is done outside of.
Yeah. So all this code is still like useful for even if you want to do that. You would basically just want to remove that set yaw angle to 0, and then you would just want to be like keeping track of what angle you're turning to. So yeah, does that answer your question?
So kind of
Yeah.
put that in a few different words for others also to get it, right? So the question was, isn't it better to keep track of how much you've turned and keep fixing your errors? So for example, if you turn 91 degrees and next you wanted to turn 35, instead, by keeping track of how much you actually turned, you could keep make that 34 instead of 35. You would still use the same my block, but you would, yeah.
I have another question. So in your code, it says ABS. So what does ABS mean?
Oh yeah, ABS just means absolute value. Have you like learned about that in school yet?
Yeah.
Okay, yeah. So it's basically just saying instead of like 2 or -2, it's just saying like your distance away from 0. So like -2 is the same as 2 essentially.
Okay.
So I saw in the chat about gyro in, gyro out variables. So I haven't actually heard of those. But I mean, I'm assuming
names for the variables.
I'm not sure, but I'm assuming those might like yeah, that's a way of keeping track of your like total like angle.
Oh, wait, can you get more context? Is that the name of variable from that
Yeah,
program?
yes, okay, yeah. So I haven't heard of those, but those seems like that could be useful for like long runs. So yeah, you if you want to like use a total angle counter approach, you could definitely try and like look into something like that. Okay, all right. Yeah. I'll just go right. All right, so we'll our 15-minute break will be over in about 2 minutes. So yeah, we'll like start back up.
So can you explain like why is it the less than equal than 2? Less than equal to 2?
Oh yeah. Okay, so this less than equal to 2 part, if you remember from our basic gyro turn, we had this like thing for overshooting, this like -11. So the thing is, it's the exact same thing. Even with like this P control turn with decelerating and all that, right? The thing is we're coming to a stop from a speed of like 5% to 0. So within that, there is about like 2 degrees of overshoot. So that's what we're doing. We're accounting for that. We're basically stopping the program 2 degrees early so that the overshoot just takes it to our actual like target angle. Yeah, also for each robot, this value will be a little bit different because if you have like a very heavy robot, it might overshoot a bit more because there's more momentum versus if you have like a very light robot, it might overshoot less. So, based on your robot, you will have to like, you can play with this value. So the way I'd suggest doing that is run the program and then click on the thing up here. I'll show you guys.
Pretty cool. I don't know, never seen a robot like that, but
Right,
you
so
would basically
basically,
tune those values depending on your robot. So if your robot is light, where you have like very
so what I'm gonna do is
you would just like lower those values.
set it to 90 degrees, run the program. And so now it finished turning and it stopped at exactly 90. So that means that we don't need any, like, we don't need to do anything. But say I made this 0. So basically, say I didn't like have any overshoot counter. So now I'm gonna run the program. And it overshoots by 2 degrees. So that's how I know that I need to basically put in, I need to stop at 2 degrees early.
Can you run it again?
With a 0 or a 2? Yeah. Why? Yeah, so now I put the 2 back in and it's at perfect 90.
Now, just one more thing to add is it is quite possible that without having that compensation, you can still run this. But what will happen then is it might overshoot and then come back. So you will lose some time in that correction, that auto correction. And is that not in there? Because if you have any absolute error, it corrects it.
It'll pass by you this and stop it. Passes by this and stops. It's greater than or equal to that.
And that's the absolute one.
Oh, yeah, I'm just gonna do one last thing before we move on. So, all right, yeah. So basically, if you guys like look up here, I'm just gonna run the program with the robot in my hand. So right now this is like a really good way to demonstrate like the deceleration. So right now we're at like, it needs to turn 90 degrees, right? So if I start turning it, you can see how the wheels sort of slow down. And if I go the other way, it's accelerating. So this is basically what the proportional algorithm is. And now if I
So
get it to 90,
basically, as we're turning, like the speed changes it as well.
yeah. So like the overall way to think about it is as you turn, like as you get closer to your target angle, your speed decreases. So like when you're turning 90 degrees, when you first start, you have 90 degrees to turn, so you're gonna be turning quickly. But then once you get to like 10 degrees left, like so you're at 80 degrees, your speed's gonna be a lot slower. All right, is everyone ready to move on to the going straight? All right, yeah, in that case, we'll move on. So go back to the PowerPoint here. All right.
May I
So-
ask a quick question?
Oh, yeah, sure.
Finally, I've been I'm a parent and a coach, and all of my kiddos are in class today. So I'm curious if this meeting will be recorded and if you guys will be able to share it.
Yeah, we're sending the recordings out to everyone who signed up. So yeah,
Thank you.
you'll get the recording.
And then the next question was specifically, I had some kids ask about the slippage on the wheels as they start their launches. There were some ideas that we found online about like trying to physically back the wheels out to in the starting area against the wall, or driving back very briefly, a few rotations. Have you guys experimented with that, or do you know of any techniques that can help avoiding the initial slippage of the wheels as the robot starts?
Yeah, so I mean the easiest way is like what we're doing here is we're setting the movement acceleration to slow, but this like might not be enough. So you can get like really advanced, which we're not going to cover that in this class, but you can.
Let me add a couple of things.
Yeah. Yeah. So what I was saying is you can get really advanced, and basically add like a proportional algorithm to your speed, like your forward speed also. So like basically what that's saying is you want to like start off like you're basically accelerating rather than just going straight to like 50% power when you're moving forward. You have like an algorithm that's starting you off like 10%, then like 20%, then 30, then 40, then 50.
Okay, yeah, we do that already. Okay, I was just curious
Yeah,
in terms of just something easy to avoid the slippage, but I think you've given me a direction. Thank you.
Okay, yeah.
So just a couple of things to add is there's two things. One is avoiding it, and then if it has happened, how to fix it. There, like I mentioned in the very beginning, there are some teams that back into the edge of the uh, perimeter of the whole FLL table to know exactly where they are. And I've seen that kind of reduce, like not many teams do that anymore. Part of it is with the Spike Prime and them having provided this ability to accelerate at different speeds, because back in the EV3 days, there weren't any blocks which helped you change the rate of acceleration. So, back then it always just started off, but there were some teams who used to intentionally start at a slower speed and then have another block where it was slightly faster. So in a way, achieving that slower acceleration through multiple blocks. But now with the ability to use the slow acceleration block, it should largely take care of that. Have you used this and still felt there's wheel slippage going on?
Sorry, I had to unmute myself. I think your explanation with the EV3 makes sense, and I'm thinking the research that was done with this was found with EV3s. So I was looking to see if that translates into Spike Prime, but no. And then I'm looking to teach the kids the acceleration, and we have proportional acceleration course and deceleration course set up as well. But I was just looking for any other additional strategies or ways that that you guys knew of, and it looks like that particular case, setting tension on the wheels as you launch, or driving back, seems like it's no longer necessary.
No, but that proportional acceleration, it's definitely a really good thing to teach the students, because once they go into the other programs like FTC and FRC, they could definitely leverage that knowledge, because in out there, they're going to be writing lines of code from scratch, right? It's not block coding. So definitely out there, this would be useful. So
thank you.
Yeah, definitely teach that. Yep.
One like final thing, if you're noticing like a lot of slip, is just like reduce the speed that you're moving at. That seems to make stuff more accurate. Yeah. All right. So with that, we'll move on to PID drive strips. So till now, we've been using something called proportional control, but the thing is, proportional control is actually just like a third of something called the PID algorithm. So that's what I'm just going to discuss really quickly. So there's three parts to the PID algorithm: proportional, integral, and derivative. So in robotics, the proportional is like sort of the main thing you need to use. Integral and derivative are, I'd say they're pretty optional. Like when we were in FLL, we experimented between like using all three versus using just the proportional. And we found that just proportional control was like enough. But these concepts are really useful, especially in like FRC, for example, because anytime we have an arm that we have to move, we need to use like all three of these values to make it accurate. I mean, in FLL, it's you don't need to use on any arms, but it's a very good like concept to know. So a proportional part, which is what we've been doing, is it basically uses, so it takes the current error in the system and it makes a correction based on that. So like we have a 5-degree error, it's gonna make like, say like a 10% correction versus now, let's say we have like a 10-degree error, it'll make a 20% correction. That just as an example. Now integral, this is a new thing that we haven't talked about yet, but what it does is it uses the sum of all your previous errors. So what that means is say we're like driving straight and the robot seems to always like drive to the left a little bit rather than driving to the right. But because it's using the sum of all the previous errors, it knows that the robot likes to go to the left more. So it's gonna add that in like as a correction in addition to the proportional. And now derivative, which is the last one. The way this works is it checks how fast your error is changing. So say like in one loop, your error changes by like five degrees. So that's like your rate of change of error, like 5 degrees per loop. And so it uses that value to add like an additional correction. Does anyone have any questions about this?
I have one question. So when you say PID used to like accurately control mechanisms, so
Yeah.
like this code we recently, the last one we just did,
Yeah.
is that like PID?
Yeah, so the turning code, that doesn't use PID, that uses just the P part. It uses just proportional.
Oh, okay. So there's like different parts.
Yeah, so there's proportional, integral, and derivative. So the thing is for turning, you can't really use integral and derivative because I'll explain a little bit more why like later on. You can only use proportional, and that's like all you really need to use. But for going straight, you can use all three. Does that answer your question?
Okay. Yeah.
So I'll just give like a quick real life example of this to hopefully make a little bit more sense. So say you're riding a bike and there's like a straight like line that you have to ride your bike on, right? So now say you like veer to the left a little bit by like say 5 degrees. So proportional is gonna use that error, right? So now you have a 5 degrees error like from the line that you're supposed to be on. So that based on that 5 degrees, it'll make a 10% correction to the right. So that'll help you basically come back like onto the line. Now integral for that, say you veer 5 degrees and then like again you like veer 5 degrees to the left. Integral basically keeps track of all those errors. So it's adding all of that up. So the integral value would like then be 10 if you've gone to the left by 5 degrees like 2 times. So it knows that you like to go to the left a lot. So it's gonna add like an additional correction to the right to make sure you're not doing that.
Is that helpful for like if you're having if like in a competition you're on a different table than you normally at and your table's a little slanted?
Oh yeah, that's actually a really good example. Yeah, it would be really useful for that. Because yeah, when you're slanted, it would cause your robot to start going to one side more. So yeah, that's like it would help you correct that. And then oh wait, Bryce, you have a question? Or oh sorry, I think that was you. Oh yeah, my bad. All right. Yeah, and then so for derivative, now say you're riding your bike, right? And say you like veer off to the left like 10 degrees. And then now say you're proportional and integral, it's correcting you to make you start going to the right. But say because you had such a big error of 10 degrees, you start going to the right like too quickly. that's what derivative helps with. It basically like smoothens that out. So if you start going to the right like too quickly that you're gonna overshoot, it's gonna slow down your correction to basically smoothing out the system. Does that make sense? Yeah, in that case. Does anyone have any final questions about this? And also a lot of the
I have one more.
yeah, go ahead.
Yeah, like I have one more question. So just double checking. If we like like in your previous code, it's like, oh wait, actually never mind. Never mind.
Yeah, that's fine. So also a lot of these will like the integral and derivative will make a lot more sense once we like get to the actual code because you can once you see like the calculation you use, you'll kind of understand what I mean. Like when I'm talking about these. All right, so first we're gonna start with it's not the integral and derivative quite yet. It's just the P control gyro straight. So this will basically help you understand like the logic behind this like gyro moving straight code. So I'll just quickly go through it like on the screen. So basically what we do is we have two inputs. We have speed and we have degrees. So speed is your movement speed. It's how fast you want the robot to go. So like I think the max speed is 100%. So if you put that, the robot would go really fast. And if you put like 20%, the robot would move pretty slow. And then degrees is how far you want to go. So it's literally saying like how many degrees you want the wheel to rotate. So if you put like 360 degrees in, it would mean that your wheels will rotate like one complete rotation. And if you put like 720 degrees in, that would be two rotations. So yeah. Do you have a question?
Another thing. So you mentioned PID. So does like PID like does it stand for anything? Or
Oh yeah, the PID it stands for the PID stands for proportional integral derivative.
okay.
Yeah.
So it just helps you do it more accurately. Like if you're turning to a specific, like for example, if you're turning into like a right, and if let's say you had to turn 60 degrees and you had to go pretty like fast to like not waste your time and lose precision tokens, all that, like so then you would like, and then the robot would make it faster.
So PID is not used for turning at all. Right now we're talking only about like moving in a straight line, like moving forward, not turning. The turning, I'll explain why later, but you can't use the like full PID for turning. You can only use P control for turning. So this is just for driving straight.
So yeah, just to maybe take a step back and clarify when or why we need the PID algorithm, right? Now, you might have all seen this. When you're having your robot drive straight to go reach some point, when it might work once and then another time you might see that it's a little off. It has turned slightly in a different direction and gone a little off from where it was supposed to go, which means it did not maintain that exact straight line. It either went a little to the left or a little to the right. And that's what we are trying to address by using the PID go straight algorithm. So what we are doing here is using the PID algorithm to ensure that your robot has gone in an exact straight line. And in fact, you'll see once this code is put in place and during the demo, if your robot is driving straight, you give it a little whack, it'll turn right because of the force of your hit, but then it'll turn back and go straight again to where you intended it to go. So that'll illustrate how the PID algorithm ensures that your robot continues to go straight, even if it hits something. And of course, in FLL, it's not that somebody's going to hit it or some mission model is going to get in its way. It's more due to inaccuracies of the motors. If it starts going a little left or a little to the right, you will use this code to bring it back to being exactly straight and go where you want it to. Okay.
All right, so I'll just go through this code like briefly. We'll go through it a little bit more in depth when we're actually making it. But we start by just setting our movement motor positions to 0 because we need to, that's how we like determine our degrees, right? We put in like 360 degrees. So we need to set this to 0 first. Then we just set our yaw angle to 0. And then this should look familiar. It's just movement motors, setting it to brake. And especially when you're going straight, having that brake mode is really important because you want to make sure you're not like moving too far forward because that could really make it inaccurate.
Could we put it at the beginning of the program?
So all of these blocks here, it doesn't really matter what order you put it in. They're sort of like, they're not dependent on each other. They're just like
I mean, like
individual.
when the program starts, you put those on
Oh,
before
yeah.
you define
yeah.
the function.
Yeah. For the when program starts, yeah, you can just put it like there, and that way you wouldn't really need to have it in your my blocks. Yeah, that's correct. All right, so then now we're setting some variables. So the first variable we're setting is just our target angle. And the reason we're setting it to 0 is because up here we set our yaw angle to 0, right? So that means that like now when we move in a straight line, we want to make sure that our robot is staying at like angle 0. Because if it's moving to like angle 1, 2, or like -1, -2, that means that's going off course. So our target angle is going to be 0. And then now KP, I'm going to go back to the turning code to just like explain what KP was. So here, the KP value was this 0.5 right here. So what it is, it's basically the number you're like multiplying to your error to get your speed. So that might not have made too much sense. Let me just like repeat that. So we said that for the P control, right? Our speed is proportional to our error. So that's what this is doing here, right? Setting our speed to our error times 0.5. And the reason you need the 0.5 there is if you just set your speed to your error, it might make the robot way too fast or way too slow. So you sort of need a value to get the speed like within a reasonable value. So that's what your KP is doing.
Does it depend on the circumference of your wheel, or the distance between the center and the outside of the wheel?
So those are actually both things that could affect your KP value. So the thing with the KP value is you need to like sort of tune it. So say like your robot's really heavy, you might need a higher KP value because you need more force to actually turn your robot. But say if your robot's really light, a higher KP value might make it turn really quickly. So, and then also wheel circumference, if you have a bigger wheel circumference, that means that your robot will move quicker. So you might want to lower your KP value. And the distance between the center and your wheel also affects it. Because if that distance is bigger, it means that like to turn, your wheel has to actually rotate like a higher number of times.
So I heard you say something about KP. I don't clearly understand what that is.
Okay, so all right, I'll try and explain it again. So you know how with P control, we set our speed to be proportional to our error, right?
Mm-hmm.
Yeah, so that's basically happening. Let me just go back to it. Yeah. So we had like in this section, in this block right here, we're setting our speed to our error times 0.5. So this 0.5 here, that's just what your KP value is.
So,
Okay.
so let's put it in a few different words. Now, you know that you have an error of certain degrees, and you want to apply a certain correction. Now, degrees and power, they're two different things, right? They're two different, they're not like,
Two different units.
yeah, they're two different units. And you can think of it as two different units. Now, there needs to be some multiple that makes them equally proportional or proportional. And that is what is KP. It's the factor of proportionality that needs to be applied. So for example, let's go back to going straight. When you're going straight, let's say that your gyro sensor detected that your robot is off to the left by 2 degrees. Now the number you have available to you is 2 degrees. How do you translate that into a certain amount of power that you give to the robot so that the wheel has, the two wheels are now being given slightly different power so that it moves slightly to the right to correct the error where it was to the left. Now, translating that 2 degrees into proper amount of power, that is something you determine based on your robot. And that factor, that multiple that you're going to use, that is KP. And what we have here is probably something, when you use that, you'll find that your robot will probably use something similar. It won't be off by too much. Like you won't have a KP of 5 on one robot and 0.25 on another robot. It's not going to be off by that much of a factor. Does that help in understand why we have this KP?
Yeah. So if the robot's smaller, would we want our KP to be bigger?
No, it would probably be slightly smaller, because if you give too much of a correction, then you're going to cause an error in the other direction, right? So that's why you'll play around and figure it out. But what I would suggest is use the value we have, see how your robot behaves, and then tweak that number like by 10 to 20%. Increase it 10 or 20% or decrease it 10 or 20% and see the behavior.
Yeah.
In fact, yeah.
We'll when we run this program here, we'll demonstrate I'll put the KP really high and you can see what happens. And I'll also put it really low and you'll be able to see what happens. So that should help you guys now understand a little bit more about how it works.
Okay, and I think we had a question in person here.
The robot going, if you bump on it, will it still goes back?
Yes.
Yeah, it will correct itself.
Go back. Yep.
All right, so now let's I'll just finish explaining this program. Yeah, so we're setting our KP, and then now, so the thing is we have two motors sort of giving us degrees, right? So we're tracking the movement of two motors. So the most accurate way to be able to tell if we've reached our target of 360 degrees is to track the average of these two motors. So that's why we made a variable called average degrees. So now in our repeat loop, we're going to basically repeat until the average degrees is greater than or equal to our target degrees that we had put here. So that's just our end condition. That means that when this is true, it's once we've moved one rotation, we're going to exit this loop and stop moving. So now in the loop, the first thing we do is set our average degrees to basically, you guys all understand how average works in math? Yeah, so you take, if you're finding the average of two things, you add them up and divide by 2. So that's what we're doing here. And the thing is, we have to multiply one of these by -1. And the reason for that is because when your two wheels are moving forward, the motors are facing in opposite directions. So even though your robot is moving in one direction, one of the motors is actually turning the opposite direction compared to the other motor. That's why we're just multiplying it by -1. To make sure they're both positive. All right, and then next this is our P control. So our target angle was 0, right? Actually, sorry, this isn't our P control. This is finding our error. So our target angle is 0 because we reset our yaw to 0. So that means that's the angle we want to stay at when we're moving forward. So we do our target angle minus our current yaw angle. So say we're veered to the right by 2 degrees. So that means our current yaw angle would be 2 degrees. So 0 minus 2 would give us an error of -2. And then now this block, this is our P control. So we're basically taking that error and multiplying it to the KP value. So this is really similar to what we did in the turning over here, where we set our speed to the error times 0.5. Here, instead of setting speed directly, what we're doing is we're setting our direction. So I'll get into that when we're actually building the program. Yeah, and then that's it. So it'll keep repeating this. And once we reach like our target degrees, we'll stop moving. And there's just an example of how you use it. You could put like a 50% speed and then 500 degrees of rotation. All right, so now I'm gonna get into building the program. So 1 second. All right. So we start by just making a mod block, and we can call this heat control drive rates. Mini water. And then we need the input of speed. And then now, because we have two inputs, you might forget which one is which. So that's why you can add something called a label, which will it'll just show up like this on your my block. So it makes it easier to tell which input is for what. All right, and then now we need degrees, and then we can add another label. That's good. So now, yeah. All right, so now the first step was setting our motor degrees, like resetting them. So you can do that here. So this is why we had to add the more motors extension. It's so that we could get this block. You basically set your relative position A to 0 and relative position E to 0. And the next step is just our yaw angle. Oh, yeah, set yaw angle to 0. And then now we need to set our movement motors. So I'm just going to copy that from the old one. Yeah. Oh, yeah, go ahead. Yeah, you can, what was your question?
You don't need two blocks at the start. You can remove one of the blue blocks and press the drop down, press multiple, and select A and B.
Oh, yeah. Oh, that's a good point. Yeah, thanks for noting that. So basically what he was saying is actually didn't realize this was a feature. You can click this drop down and select multiple. So now we can just select A and B. So yeah, you can do that, I guess, instead of using two blocks.
Two inspected removable.
Yeah, yeah.
But you're using two motors for motion, so you pick two for the movement motors.
All right, so now we need to set our target angle to 0. And then we need to set our KP. So you guys won't, I don't think you guys. Oh my God. Oh, yeah, sure. Is that better? All right. So you guys will have to create this KP variable. Just basically make the variable and then KP. And now we need to set average degrees to 0. And now we can drag out the repeat until block. And now we need to set up like greater than or equal to. We need to check if our average degrees is greater than our target degrees, or if it's equal to our target degrees.
Zoom in so that see it.
Right.
Is it
Need
hard to work
space
with?
to, yeah.
Okay.
And then now we need to, in the loop, we need to set our average degrees to the thing from earlier. So basically we need quite a few blocks. Divide, add, and basically for our robot, based on how we wired it, the number we need to multiply the A motor by -1. For you guys, it might be like different depending on how you wired it.
Can you repeat what you said?
Yeah, so I said for the robot we have, like the way we wired it, the A motor is the one that we need to make negative, like the A's position. Uh, if you guys wired your robot differently, then it might be like the E. But just like for our robot, the A is what we had to do.
Basically, the ports that you're using will depend on which ports you connected your movement motors to.
How do I figure out if which one is supposed to go which? So like if A is supposed to go on the left or E is supposed to go.
Oh yeah, so always all right. So for this movement motors, did you just have A plus E? Like, did it look the same as our block?
Yeah, similar. It's A plus E. I mean B.
A plus B. Okay. So if it's A plus B, then what you would have to do is instead of using E, you would want to use B.
I see.
And also make sure that over here you're selecting A and B instead of A and B.
Mm-hmm.
Yeah. All right. So now we need to set our error. So the if you wait, Norman, did you rename the error variable?
Yeah.
We need to make a new variable.
In this case, it really is error.
Yeah. So let's set error to basically our target angle minus the current yaw angle. Yeah.
Question I think asking if you any acronym.
Oh, what?
KP is an acronym.
Oh, so KP, it's not an acronym. It just means it's like what it's called is the proportional multiplier.
I have a question.
Yeah.
What does it mean by the last error? An error?
Oh, the thing you saw here. We'll get to that later. That's for PID. That's for the derivative portion. We'll get to that in a little bit.
Target angle minus.
So do we just put the same error in all of them?
You mean like this? Oh, the
Yes.
same error variable? Yeah,
Yeah.
you can use that variable. Yes. Yeah, so for this start moving block, you're gonna want this one. Because we're basically making the P control change the direction we're moving. And now we just need to do our error times the KP value.
I have a question. So like
Yeah.
in the repeat until, like the first code, like the green one, it says degrees bigger is smaller than average degrees, and then or. So do you put the one that says degrees is smaller than average degrees, that one, do you put that in like the Did you put that in like the orth one?
Oh yeah, so basically, all right, actually, you know what? I'll rename the average degrees variable to make it a little bit, hold on one second. Oh, one second.
Star
Yeah, so the average degrees is our current, it's like how far we've currently moved for. And then the degrees, that's like our target. That's how far we want to move. One second, I'm just gonna mute everyone. There's a lot of background noise. Okay. All right. Yeah, thank you for muting. Yeah. Yeah. One second, guys. Gonna if I click make host, will it make him the host or will it make him co-host? I think, I don't think we can focus. So, all right, this should be the complete program. So we can go ahead and test it. I'm just gonna drag it. And now you guys, it's completely fine if you guys haven't finished copying it down yet. I'll still keep it open here. So key control drive straight. So say we want to move at speed of 30, and then I'm gonna make this like really long, move for like 1500 degrees, and we'll basically drive it across the table and show you guys how it works. You guys watch here. I'm gonna knock it, and then it's gonna wait. Change the speed to like 50%.
I have a question.
Yeah, go ahead.
Is average degrees a new variable or can it be written as error?
Average degrees for Hans. Average degrees is a new variable.
Oh yeah,
Average degrees is a new variable.
Okay.
How does the degrees work? Is there a way to convert the degrees into like inches or centimeters?
Yes, there is. I think Rohan can explain that more in detail. Oh wait, converting degrees like into the centimeters.
Oh yeah, so it's completely like possible to use degree inches or centimeters instead of degrees. What you have to do is you have to basically know the circumference of the wheels you're using, and then so say your circumference is 2 inches. That means that 360 degrees would convert to 2 inches. So you'd have to have that calculation in your code. We would suggest using degrees. Yeah, our suggestion though is just using degrees because it keeps it simpler. But yeah, we have seen teams do that. All right.
How would
Sorry, what was that? Were you asking a question?
So
right?
does degrees mean the distance?
Yeah, degrees is essentially the distance you're moving. So the way it translates to the robot is it's like the amount of degrees that your wheels are turning. So say if you put 360 degrees, it means your wheels are moving one rotation. Um, are there any last questions with the P control drive straight?
Can you keep it on for a little bit? I'm still copying it down.
Oh that's completely fine. I'll keep it on. And then if anyone like online was testing this on their actual robot, let us know how it went. Uh, 1 p.m. We got 30 minutes left.
I don't understand. Like, not under, like I can't like when you did repeat like your feet first repeat until you will
Yeah.
degrees smaller than average degrees and then so on. Like,
Oh
can you
yeah.
show us how you did that? Because like I don't get it.
Oh, like do you mean the actual code or what it means?
Like, how did you put it together to form a graph?
Oh yeah, I'll show you. So basically what you have to do is you have to grab out an ore and then you need this block like the left you need either less than or greater than and you need an equal to. So the degrees you get it from up here and you will put it like in there. And then average degrees, if you create you should like you got to make sure that you created a variable for it. And then once you have, you can just drag out average degrees. So basically it was like that. Then you just put that in there and you just put this in there. So now what this is saying is
Okay.
you're going to repeat until your target degrees is less than or equal to your current traveled like average degrees.
All right.
Yeah. We'll give everyone like another minute or two to finish copying this down because we do want to make sure that we get to the final portion, which is the full. Oh yeah, sure, yeah. Do any of you guys want to run your code on the robot? Go ahead.
My program doesn't seem to be working. I put in 5,000, but it never stopped. And I put in but it worked for like 1,000.
Oh, for you're saying 5,000 for the degrees? So 5,000 degrees it's like a lot. Like it's probably gonna take like 15 to 20 seconds to like run 5,000 degrees. So I'd say just lower your value. So like if you said 1,000 degrees work, then it should be working. Like 5,000 degrees is probably like 4 FLL max. So pretty long distance. Well, unfortunately, that actually doesn't really make it any faster than if you just put 100 in. Because they're limited to like 100%. So any number above that just gets plants. Yeah, I'd recommend not doing that. Probably be better for your computer. All right, at this point, we're gonna move on to the full PID. So we'll go back to the presentation here. So this looks like a little bit longer than the thing before. The thing is, the logic is really similar. I mean, like, we're literally gonna reuse like half of the same code that we already made. We're just gonna be adding in a couple of stuff. So basically you can see like this whole first part is basically the exact same. And also setting target angle, setting average degrees. That's all the same. But now we have a few new variables. So we have integral, derivative, last error, ki, and kd. So ki and kd, those are like basically the exact same as kp. You're gonna multiply your ki value to the integral and the kd value to the derivative. And last error, what that means is like it literally means like the last error you had. So say like you're in a loop, right? And you realize that your current error is 5 degrees. Your last error could have been something like say 7 degrees or like 2 degrees. So it's a previous error you had. So what we're gonna do in the repeat until is we're first doing the same thing with our average degrees. And also this condition is the exact same. So we're setting our error again the exact same way as we had for the P control, but now we have two new things. So this change integral by error. So I mentioned earlier when I was talking about PID that the integral, what it does is it basically sums up all of the errors that you've ever had. So it's exactly what this is doing. So as your robot is driving forward, it's going to keep adding, like every loop it does, it's going to keep adding your current error to the integral. So your integral value is going to basically have like a sum of like all the errors you've ever had in that like program. And then now for derivative, in order to basically the derivative, what it does is it keeps track of like the rate of change of your error. So that's why we're using last error. Where basically say our current error is 5 degrees and our last error was 7 degrees. We know that if we do 5 minus 7, our error changed by -2. So that's like the rate of change of our error. Are there any questions about how integral and derivative are calculated?
I would like to add that the PID, I know some, depending on whether you've tried to look into PID before, it might be a lot to throw on you all at once. So what I would suggest is if you are not very clear on certain things, ask us questions. But despite that, if you're feeling like you need to take a step back or go through it a little more before you totally understand, that's totally fine. You have the code, you have an explanation. The presentation slides will be made available to you. The recordings will be made available to you. So you will be able to go back and rewatch or reread these things. Hopefully that'll help you understand, when you go through it again. And for those who have done this a little before and have a kind of an idea, if this is causing you to get more questions, please ask us. We'll be happy to discuss and make you understand. Because what exactly the proportional does, what exactly the integral does, and what exactly derivative does, it's pretty interesting and may not be very straightforward to understand right away. One thing we will add is the greatest correction will always come from proportional, because proportional is correcting the error as it is right now. And integral, so your ki value will actually be a much smaller number. It's a very small decimal number compared to kp. And the reason is the integral error, if you have a huge integral correction, it's going to send your robot in a loop. You really want to use that as a preemptive correction because you already know that your robot tends to kind of keep erroring on one particular side. So you're giving a preemptive correction, and that needs to be really small. That's why the ki value is as low as 0.02, whereas kp is a much larger decimal number than that. And for derivative, again, that is not going to be a very large number. It's going to be larger than ki for sure, but please understand that derivative is, again, it's used so that it smooths your corrections. Otherwise, you'll find that sometimes when you apply PID, it's going to oscillate because it goes the other way. And now it's like, oh, I applied too much of correction. Now let's go the other way. And your robot's going to start oscillating. What derivative does is it helps reduce that and act as a dampening effect and make that correction be more gradual so that it stops oscillating.
Is the KP, KI, and KD all different for different robots?
Yes.
Yes, yeah. They will all be slightly different for different robots, yes.
But I would say the value.
How will
Yeah. Sorry, I was
how
just
will
going to finish
you?
up saying the values we have there, you should definitely start with those. And then depending on the behavior, you would start correcting it. And like we said, for most purposes with FLL, just the proportional is all you would need. If you have some really bad motors which are really going, veering off in one direction all the time, then the KI and KD would help. That is, having integral and derivative would help. But I would strongly suggest if you have such bad motors, actually replace the motors rather than trying to fix it entirely through code. But for the purpose of understanding and for your, this will definitely apply in future when you do FTC and FRC. Hence, having a decent understanding of the whole PID would be useful.
Yeah, and what were you saying earlier? You can go ahead. Were you like asking a question earlier? Or did we like answer everything that you said? Okay. All right. Yeah, so in that case,
I
I think
have a question.
yeah, go ahead.
It's actually it's actually kind of related to the code. It's actually kind of different. Like when you're using your robot, I noticed that you use the advanced driving base, and I was
Yeah.
wondering if like you think that that's a really good robot to recommend, especially for like this season.
Yeah, so I'd say like if it's your first season of like first year of FLO, it's a really good robot to like start out with because there's already instructions for it. Like you don't really have to, and there's already attachments built into it, so you can sort of skip that whole process. Uh, but I'd say if you're a bit more experienced, you could look into other robot designs that have sort of like more flexibility. Like when I was in FLO, like we were using a decently advanced robot, which it was called like an XY robot, where basically you had like a huge like sort of plate on your robot that could move like side to side and up and down. So that allowed you to do like, a lot more stuff with it, rather than just like flicking something. But the advanced drive base is still like definitely it's a pretty decent robot. But it's
And yeah, some more considerations should be the size of the robot. So the advanced driveways would be slightly larger in size than many teams might design their robot to be. Uh, but like Rohan mentioned, the fact that you have attachments and I mean you don't skip the design process. Obviously, you go through and you plan, but it makes you get ahead sooner than if you were to start with a robot from scratch. And then if you are an advanced team and you are used to building your own design robots, then a more compact robot, and also, one more thing to consider is the concept of box robots. The idea with box robots is you have a couple of gear mechanisms which come up there, and then you drop a whole attachment on there, which is an active attachment, which means the gears will make connection with those box robot gears, and then you are able to make your attachment accomplish whatever you need. That way, you can remove that entire attachment and then drop a whole new one simply on your robot. And that way, you're able to very quickly change your attachments, and those attachments can be really custom built for the exact missions that you want to solve in that specific run when you're using that attachment.
yeah.
Again, it's really the team has to decide, what direction you want to go.
Yeah,
And
like there's an example of a box robot where like to the blue part, that's like the robot itself, and this whole gray thing, that's all one big attachment that they just slide onto the robot. and it's connected to some like gears that are sticking out, and that's basically powering the mechanisms. So I'd say a box robot is definitely the most advanced and probably like the hardest to execute robot design, but it is definitely powerful. It is like the most competitive teams all have box robots.
So again, the robot itself may not be very complex, but you really have to get creative with the attachments.
Yeah.
That's where the complexity goes up significantly.
And this is another pretty competitive design. It's basically this is what the robot that I used when I was in FLO, but you can see how that plate can move up and down and side to side. So you can do a lot of stuff with it.
I've seen one that can go up and down like a foot.
Sorry, what was that?
Said he's seen it goes up and down a foot, I think. Like,
Oh wow. Oh, that's pretty impressive. Yeah, well, I'll just quickly go back here. Yeah, so I think I left off at derivative. Yeah, this was basically calculating the derivative, the rate of change of error. And then now this start moving block, it's basically we have, so this part, error times KP, that's our proportional part. Integral times KI is our integral. And then derivative times KD is our derivative. So we're adding all three of these up. So that's how you're actually incorporating that into like the robot's final movement. You literally just add them all up and put that into your start moving block. Sorry. So with that, I think we'll get started coding this. So even though it looks like a really long program, it shouldn't take too much time because we can copy paste this entire thing and just add on to it. So ID, gyro, rod. Wait. We need our speed input. We need our degrees input. And yeah, so we have this. So what you're gonna want to do is just duplicate this entire thing and drag it here. And then now we'll start to add on. So wait 1 second. I'm just gonna take a picture of that. Okay. All right. Yeah, we're just gonna get started encoding. So we need to set our we're gonna need to drag out a bunch of these set blocks. Enough. So we need to set our integral to 0. We need to set our derivative to 0. We need to set our last error to 0. And then now we need to set our here. So Ki, we're going to put it to 0.02. And Kd, we're going to put it to 0.3.
What does K stand for though?
It doesn't necessarily stand for yeah, you can think of it as constant. So if you've heard of like a constant in math, that's usually
Yes.
Guys, your brother's still in the class.
I'm just gonna mute you guys. Okay, KP, KI, KD, and then so we set our average degrees. Yeah, so now we need to drag out the change block. We're gonna change our integral by our error. And then finally, we need to set the derivatives to error minus last error. And now over here, we need to grab 3 plus blocks. and just put them inside each other like that. And then now we also need more multiplication blocks. So this is the proportional, and this will be integral. And, yeah. Integral times ki, derivative times ad. Yeah, and so that's all. We're already done with this full PID one. So on our end,
Keep
we're gonna go
longer.
ahead and run
Excuse me? Can you go
Yeah.
can you please go back to the code? I wasn't done.
Oh yeah, sorry, yeah.
Yeah, zoom in and keep it.
Yeah. So we do have one of our in-person campers demoing, so you guys can look at that. So it'll look really similar to the P control drive straight. But yeah, you guys can.
Once you open this, you can just connect them.
Yeah, well, wait, can you turn on just hold on Bluetooth? That's done now.
You're going to use the correct one.
All right, do a speed of 15. All right, so if you guys look at our camera stream, I'm just gonna go there. You guys will be able to see.
Let's run that again and show how it is going to be.
Wait, no, I'm just taking it off first.
So you guys saw how. Yeah.
I
Question?
have another question. So, like after you make a really big code next to it, it says program starts and then there's something underneath it. Like, is that just like a simpler version of that big one?
Oh yeah. So I mean, you're talking about this block?
Yeah.
Oh yeah. So this whole like big piece of code here, this is like defining our my block. But once it's defined, it means that like you can just drag it out from here and basically. So yeah, it is a simplified version. When we use this, it just means it's gonna run all this code. But you just have to drag this out. You don't have to recode this every time.
Right. So this one was the definition of the my block.
Yeah.
And this whole thing was the definition. And this is where you're using what has been defined. With just one block, you are using that whole my block.
Okay. And also, I have another question. I actually need to copy paste another thing onto my thing. So, I kind of forgot how to do it. Can you like?
So yeah, I think you can just so basically yeah, you could do that. Or say like you want to copy paste like this block. I mean you can just duplicate it too. That's what I did. So
So like you double click the thing.
you don't double click, you just you right click. So right click on this, and if you click duplicate, it'll duplicate this entire
everything under that.
Yeah.
Got. Thank you.
Yeah.
Just want to draw attention to one difference in earlier when we ran the PID algorithm with just the P, what we saw was if you gave it a big hit, it came back and straightened itself, but it would end up in a slightly parallel position because the hit we gave was pretty strong. So it ended up causing the robot to end up being a little more parallel. Whereas when it runs now, you see that despite giving it a whack, the correction is such that it will go back into the same straight line. So that is a good example of how integral helps you make sure that you don't end up in a parallel path. When you have only proportional correction, if you have a lot of errors, you may end up in a parallel path. You will be straight, but you may end up parallel to where you intended to be. Whereas with PID, because of the other two corrections, the fact that you are parallel is also corrected, and it brings you back to the same straight line that you intended to be in. Now, in FLL, realistically, you're not going to have anybody going and giving the robot a hit and making it roll off or turn so much off track. And you won't really run into mission models as a plan and have the mission models make your robot go too much to the side and come back. So those are unrealistic. But it's a good illustration of when PID makes a big difference compared to just the P-based going straight. Any questions regarding that? I see we have Bryce and two others have their hands raised. So let's start with Jonathan. Jonathan, can you please ask your question?
I was just wondering, inside the PID code, don't you have to set the last error inside the repeat until, or does it stay 0?
So last error is a sum, or maybe that was not done yet. Okay.
Oh yeah, really sorry. I actually forgot. I forgot to add that in over here. That's a good catch. Yeah. So basically, yeah, at the end of your repeat until, you want to set your last error to the current error. For the next loop, it's your last error. Yeah. All right. Actually, yeah, great catch. I completely forgot to add that.
Where do we use the last error? I don't see any. Oh, I see. Never mind.
Yeah.
We went set last air back,
Sorry, what was that?
Then when we set all of our things, we said the last air.
No, because this is from the.
Oh.
So, this is actually.
You can go and choose the
Oh, wow.
Does this program make the robot update or run slower?
No, it shouldn't. I mean, there is a bit more math in like the repeat until loop, but I mean the processing speed isn't that slow that it's this much math is gonna affect it. So no, it shouldn't.
I have like a question. So like the code, that long code that we just made,
Yeah.
like what does that one do again?
Are you talking about the PID one or the P control one?
The second one, like I forgot what
This
it's
one?
called. Like, yeah.
This one? Oh, I mean, well, like the overarching idea of it is it helps the robot like stay straight, like accurately. So like when you're driving straight, it makes sure that the robot doesn't veer off course.
Okay.
And it uses the PID algorithm to do that.
not. And you really just rather Even the start moving and stop moving block, it does very simple. I mean, whenever you copy the code into every single program you make.
That's the thing that you don't have to do that because you have the mod block.
So there's a question here, which is, isn't it simpler to use the start moving and stop moving, which is just the basic motor movement? So like we explained, that's exactly how teams will start. They will start by having their robot move, just using stop moving, and having certain degrees to stop at. But what we're doing, right? What we are doing here, though, I mean, you will see if you go down that path and you solve your missions, you will start encountering situations where your robot's not ending up in the same spot every time. It'll start frustrating you because you will see that sometimes it works, sometimes it does not work. And the advanced coding algorithms we're using here, the whole intention is so that your robot is made more predictive, right? It's going to always go exactly where you want it to go. That you're trying to make your robot precise so that it can repeatably accomplish your missions, not just once in 5 runs or three times in 4 runs or something like that. You want it to ideally work every single time, and that's why you're using these algorithms. Yes, they are complex, and yes, you have to learn and understand how they work. But once you've done that, you will be able to reuse this code in all your programs by using my blocks. So I would say understanding it is, in fact, the more important thing than worrying about, oh, that's a lot of code to reuse again and again, right? Okay, we have a couple of questions here in person. We'll cover that, and then Shreya will come to you.
The morning was great. They fix what problems and make them.
Right, exactly. So yes, speed control would make your robot more reliable because, as you said, you may build a mission and build a piece of code to follow a mission, and then if it's not working every time, you make corrections, and then those corrections may not necessarily mean it'll work every time again. Whereas when you have something like a P control or PID control set of turning and going straight, you are taking care of those potential errors. Okay, yeah, you want to go ahead with your question? You can go.
No.
Okay, we'll come back around to you. Shreya, please go ahead with your question.
So all of these are advanced coding algorithms, right?
Yes, that's correct.
Okay.
And there may be a few more, and you will, as you go ahead, you can modify some of these to come up with your own, different set of algorithms. But the common thing, as you saw here, is the whole PID, right? The proportional correction, and then proportional integral and derivative correction.
Can you
So
show all the algorithms again?
yeah. So yep. So what we saw was, so the PID gyro straight was what you saw just now. And before this, you had the P control gyro straight, where we used only the proportional part. So these two are for going straight. And then if you go back up, this was, of course, just an explanation of PID algorithm. And then let me go back and start from the beginning. So we had the basic gyro turn where you simply use a gyro sensor to do your turns without any other algorithms, just using gyro. And then we covered the P control gyro turn, where you are proportionally controlling the speed of your turn, which made it more accurate. And then we covered the PID go straight first with the P proportional only, right? And then we did it with proportional integral and derivative, all three of them included. Does that answer your question, Shreya? Okay. I think we have Jonathan. Jonathan, you have a question? Please go ahead.
I was wondering, in your experience, would you say that Python is more accurate than Scratch?
So I would say using Python definitely gives you finer control on how you accomplish things. And I would not necessarily, I mean, you can definitely write block code, or you can put together block code, which is as reliable as Python. There's no reason to think with block code you cannot accomplish the same level of reliability, as long as you use the right algorithms.
I'm just wondering, in your experience, is it worth it?
Well, see, in what I've seen is I've like I said, I've coached FLL, FTC, and FRC. Definitely, as a student, if you want to start learning Python and start coding in FLL with Python, I would say go for it if you have the resources and coaches who can help you through that. Because the sooner you're learning these things, the quicker you will be able to accomplish similar things in FTC. For example, in FTC and FRC, in FTC, you use Java for coding. You can also use block coding if you want, but Java is an option. And then in FRC, along with block coding, you have Java and C++. So you can learn more languages as you go along if you wanted to do that.
I have one thing. Can you go to the PID Gyro straight one?
Yes, PID Gyro straight. Yep.
Yeah. Okay, give me 1 second.
Sure. You had a question? You can go ahead if you had a question.
So, the PID Gyro straight program also stops babies from using it as toy because when they try,
thank you.
It just goes back when they will likely make all babies cry when they try to play with it while the program is running.
Yeah, I think FLL robots probably not a baby toy, right? You want to be at least. Yeah. Okay, with this, that was the last of our slides, but we want to open up for questions at this point. So, any questions? We really hope that we covered what helps you through your season, and we hope that this is kind of what you were hoping to get from this camp. So let's open up for questions. If you have any questions, can you please come and go ahead and start asking questions?
I don't totally understand the start moving block at the end of the repeat until.
Oh yeah, I can explain that. So what it's doing is in the previous few blocks, right? We calculated our proportional, integral, and derivative, right? So first of all, this is like start moving block. It's a like direction block. So this is like what the block is. It's basically telling the robot which direction to move in. And so here, what it's doing here is this error times KP, that's our proportional part of the PID algorithm. Integral times KI is our integral part, and this is our derivative part. So we're literally just adding them all together, and that's going to be the correction that we make.
But doesn't that just calculate to 0 because we set all of those to? Oh, I see. Never mind.
Yeah.
Instead of putting variables there, could you have just put in like 0.8, 0.02, and 0.3 accordingly?
Oh, you're saying instead of using like KP, KI, and KD?
It uses just an extra block for each, and then it makes more blocks in your variable section.
Yeah, you could do that, but I mean, say you have like multiple of these my blocks, right? And you want to just reuse your KP, KI, and KD variables, it would be easier to have them stored as a variable. And also, it's like good practice in coding to use variables rather than hard inputting numbers. because it makes it easier to keep track of everything.
So yeah, if you guys have questions, please go ahead. Let's talk about it. Even general. Okay, we have an in-person question here. Yeah.
These box robots are so great, then why isn't there a box game?
So this one is our teaching robot, right? For our teaching robot, we feel the advanced base is a great one. So that's what we use. Okay, so let me mute the noise. So in terms of access to robots in schools and school teams, you have to work with your school teachers. Sometimes they will let certain students take the robot home on certain days, but they try to make sure it's even so that everybody gets a chance. So I would say work with the teacher, and a parent would have to take the responsibility of being careful with the mat and the robot if they take it home.
I actually have a question. Like, I was just wondering, like, do you know the schools that are going to do FLL?
So typically you should be able to find out from seniors, like kids older than you, because schools tend to, if they're doing the program already, they're probably doing it for a few years. And sometimes schools do start newly, which again, it depends on the area you're in. So we are here in Sammamish, Washington, Sammamish Issaquah area, and we know that some of the schools do have FLL here and some don't. And for those that don't, some of the FRC teams help them create FLL teams, like community FLL teams, so that the students have access to the program. I would suggest, yeah, I would suggest checking with your teachers, especially science teachers would know if the school is doing it. Yeah,
Okay,
another
thank
question
you.
here? Sure, you're welcome.
A lot of people, if a lot of people sign up, is it like a raffle or just everyone?
So in some schools, they do a raffle if a lot of people have signed up and they have limited spots. But if you're asking specifically about Beaver Lake Middle School, what they do there is they basically have a lot of teams. They have like 3 FLL teams with 10 members each. So they should be able to accommodate everybody. And then they have 2 FTC teams as well. So the max you can have is 10. So you could have anywhere from 2 to 10, but typically you'll see 6 to 8. That's the more typical number. So I see a question. Are we allowed to go? Yes. So we are done with the content we wanted to cover. Right at this point, we're just going through questions. So if you need to go, that's totally fine. We will be posting a recording of this meeting or this session, and that will be shared with all the parents who have registered the students. So thank you all for being part of this. Hopefully this was fun and you got what you wanted from this. And all the best for your seasons. But we're still open. If you have questions, please keep asking. Okay. Yeah, if your parents arrive, you may leave.